Stupid thing. Okay. All right. Good morning, chemists. Quick announcement that it's open now. Is my voice going in and out? All right. The Learning Resource Center is open between. This isn't working. Okay. So we are doing coding. All right. I hate this thing. All right. The Learning Resource Center is open now from, I think, 8 to 5 or maybe 9 to 5. There are TAs staffed in that room. During those hours, you don't need to go to your teaching assistant. All of our teaching assistants know chemistry, so any one of them can help you on lecture, homework, lab materials. And so kind of this new thing this year is that the Learning Resource Center on the first floor of Celeste is more geared towards lecture content questions, midterm material, while on the second floor of Celeste, the really nice part of Celeste, outside of the lab space, there's a TA staffed there that can help you with specific lab questions. And so again, you can go to any TA in that space to help you on your concerns, right? Okay, so let's get started now. So we left off on chapter 13, this slide, where we looked at Raoult's law, that we calculated vapor pressures of mixtures. So water mixed with a non-volatile solute, we can use Raoult's law to calculate the vapor pressure lowering extent of water. And then we also looked at calculating the vapor pressure of a mixture where both components are volatile. And so I like to think of we're actually using the same equation here where both components are contributing to the total vapor pressure. The only difference when we have a non-volatile solute like sugar, salt, many solids, is that that solid component just doesn't contribute to the total vapor pressure. It's just water. So really we're using this same equation where we need to calculate the mole fraction of the different components that actually do exert a vapor pressure. So Raoult's law follows this straight line where we change the mole fraction ratio of your solute and your solvent. So you can think, okay, if we have pure solvent A, I put in numbers from our previous example that we did. Pure solvent A, it would exert 126 torr because that's pure A. If we had pure B, just liquid B, it would exert 285. But once we make that mixture, it follows this line. Though we know that theory doesn't always match what we see in lab, what we see experimentally. And so if we actually consider the interactions between solute and solvent, if there's really strong solute-solvent interactions, we'll see a negative deviation. We'll actually see a slightly lower vapor pressure than predicted that Raoult's law predicts. All right? Okay, so there is Raoult's law. So let's look at some other properties of mixtures, and that would be freezing point depression and boiling point elevation. So we already said that when we put junk in water, when we dissolve stuff in water, vapor pressure changes how? It gets lowered. Right? So pure water has a vapor pressure, but once we start adding adding solute, so like sugar, salt, whatever, into water, the vapor pressure of water is lowered. We should have known from Chemistry 1210 that a liquid boils when its vapor pressure equals that of atmospheric pressure or the external pressure. So because a mixture is starting off at a lower vapor pressure than normal, the boiling point temperature is affected. So we get two phenomena that happen, that when we look at mixtures, specifically of water, we're mainly going to look at water here, is that when you look at a saltwater solution, the actual freezing point of that salty water is lower than that of pure water. So freezing point depression. versus that same saltwater solution actually has a higher boiling point than of pure water. So that's why we call this boiling point elevation. So salty water solutions have different boiling points and freezing point temperatures than pure water. And so it follows these equations where we use some constants to determine the extent of the freezing point depression. So you calculate, okay, how much does this mixture deviate from the normal freezing point, or how much does the boiling point of the mixture deviate from the pure solvent. And so these terms, I is the Van 't Hoff factor, K, this is the constant that we can look up in these tables for boiling point or freezing point, and then M, small m is what? Molality, yes. So this is concentration based. The more concentrated a solution is, the larger the extent of the depression or elevation. All right, so we see that here, higher concentrated things deviate more versus the pure liquid. So let's inspect how we navigate these equations. Okay, so let's look at this question, and I give you the equation for freezing point depression. Note the negative just implies that once we calculate this value, we're subtracting it from the normal freezing point of water. So actually, before we start, what is the normal freezing point of water? Pure water. Yeah, 0 degrees Celsius. So whatever we calculate here, we're gonna have to subtract from 0. All right, so freezing point depression is I times the constant for water, so that's right here, I give it to you here. This is the freezing point depression constant of water, where it gets lowered 1.86 degrees for every molal, or every 1 molality of that solution. And then we multiply that at the end here. So I didn't mention what I is. I is the Van 't Hoff factor. So we have to kind of think of the skills we used for net ionic equations. We need to think of, when we dissolve a solute in water, what actually exists as in the particle view of that water. So for example, if I put 1 unit of sugar, sucrose, in water, is this what kind of electrolyte is this? Non-electrolyte. So if I put this in water and I dissolve it, I only get 1 particle out because it's a non-electrolyte. So we say that sugar, a non-electrolyte, has a Van 't Hoff factor of 1 because it's a non-electrolyte. Versus salt. All right, salt, when we dissolve salt, NaCl, in water, what kind of electrolyte is that? Strong, right, strong because there are ions present. So if we kind of break this dissolution process down and understand what ions actually exist in water, when we dissolve salt, if I put 1 unit of NaCl in water, how many particles do I get out? Just look at the equation. 2, yeah, I get a cation and an anion. So what we see here is that salt has double the freezing point lowering power than sugar, because if I put 1 unit of sugar, or 1 unit of sugar in, I only get 1 particle out. But if I put 1 unit of NaCl in, I actually get 2 particles out. All right, so let's actually do the calculation, because now we have all of the pieces of information we need. All right, so for sucrose, we're going to take the Van 't Hoff factor we just got, so 1, because it's a non-electrolyte, times that constant that's given, so 1.86 degrees Celsius molal, and then times its actual molarity, so I'm just telling you it's 0.1, sorry, molality, 0.1 molality, all right, and then you multiply all that together, and you see that the change in freezing point, the extent it is lowered, is 0.186 degrees. And so if we subtract that from the actual freezing point of water, which is 0 degrees, we should observe an actual freezing point temperature of negative 0.186 degrees Celsius. All right. So we got to get the system a little bit colder to get this sugar solution to actually freeze rather than 0 degrees Celsius. Okay, so let's do the same thing for NaCl. All right, so just from the calculation, we're doing the exact same thing, but what is the only difference in this example for 0.1 molality NaCl? The only difference is the Van 't Hoff factor. Yeah, we get this doubling power of a salt because it's a strong electrolyte and it gives us 2 particles. So we're going to put that 2 in there that we just got, and then we multiply by all the exact same things. Molality, all right, and so we get that for this solution, its freezing point depression is 0. Whatever double that is, 372 degrees Celsius, and we're going to subtract this from 0, and so we get an actual freezing point for this salty solution is equal to something negative 0.372 because we're subtracting from 0. All right, degrees Celsius, all right. So it's always freezing point depression. Don't let the negative sign confuse you here. It's always freezing point depression. So if you know what your pure solvent's freezing point is, you're always going to subtract this number to get a lower freezing point of your mixture. All right, so without doing any calculations, what if we had a calcium chloride solution that was 0.1 molality? How would the freezing point of that solution compare to what we just calculated? It would be the same? So remember, the components of this equation, we have molality. Yeah, so molality is the same as all of them, but what's different about this compound? It has a different I value, a different Van 't Hoff factor. So can you tell me what the Van 't Hoff factor for this is? 3, yeah. All right, so are we going to see the same freezing point depression? No, it's going to be lower than the rest of them, 3 times lower than that of our sucrose one. All right, okay. All right, yeah, so let's kind of do that again, and without doing any real calculations, let's rank these from lowest to highest freezing point. So I got a bunch of stuff. And so really the strategy here is we are calculating delta TF for all of these. If we look at these variables in the equation, I might be different for them. KF, this constant, is this constant gonna be different for any of these calculations? No, so we can just ignore that value, but molality might be different for these different solutions. So our strategy is let's compare the I times M product for all of these different solutions. So why don't we just go through all of these and determine what I is for all of them. Right? So again, in your mind, look at the substance, dissolve it in water, pretend that this is a net ionic equation type of question, and ask yourself how many particles pop out when you dissolve it. So if I dissolve NaCl in sugar, how many particles do I get out? 2. What about sugar? 1, because it's a non-electrolyte. Pure water, we can ignore the IM is going to be 0, so there's no freezing point like lowering in this case. All right, sugar again, that's 1, but then magnesium chloride. This one's gonna be 3, yeah, because when we dissolve magnesium chloride, we get a magnesium 2+ and 2 chloride ions. So there's a total of 3 particles there. So we're gonna take the I and multiply it by the molality that's given in all of these examples. And so we get for that NaCl, the first one, that there is a total of 0.4 molality of particles present. For sugar, it's 0.1 because the Van 't Hoff factor is just 1. For the 0.3 molality sugar example, it's 0.3 because this is a slightly more concentrated solution, but I is still 1. And then, so what is the I times M product for that last one? 0.6, yes, okay. So these I times M products is the concentration of solute particles present in all of these solutions. So just looking at these numbers, which one is going to deviate the most from the normal freezing point of water? The one that's most concentrated, right? So it's going to be the magnesium chloride. Yeah, so now we're going to rank these in terms of freezing point depression. Magnesium chloride is going to be depressed the most. All right? Pure water has no depression at all, so it's actually going to have the highest freezing point here. And so which one's going to be depressed the smallest amount? The sugar solution, but which one? The first one, the 0.1 molarity one. So this one is only going to be depressed a little bit. All right, and so let's rank these where lowest freezing point is the magnesium chloride solution. What's second lowest? The NaCl solution, but it's the 0.2 molarity NaCl solution, or sorry, molality. All right, next it's going to be the sugar solution. That is 0.3 molality. Next it's going to be the 0.1 molality sugar solution. Sugar, all right. And then the highest freezing point is just going to be pure water. Remember, it's always freezing point depression. All solutions will always have lower freezing points than the pure solvent. All right, so all I did was, rank these in terms of the I times M product, where it goes 0.6, 0.4, 0.3, 0.1, and you can think of water as its I times M product is 0 because it doesn't have a molality. There's no solute actually dissolved. Right? So that's not, I mean, yeah, we kind of did a calculation, but it wasn't like really extensive calculation there. All right. Okay, so that's freezing point depression. Okay, so I should be able to give you any type of solute, and you should be able to tell me what its Van 't Hoff factor of. What if I gave you aluminum chloride? What would the Van 't Hoff factor for that be? What do you think? 4, yeah, because we have an aluminum, 3+ cation, and we have 3 chloride ions. Let me do another one. What if I did sodium nitrate? What would be the Van 't Hoff factor? 2, yeah, so again, use your net ionic equation skills. Understand that the nitrogens and oxygens, they don't split up. Nitrate stays together. That sodium nitrate will behave very similarly to sodium chloride. And then what about sodium sulfate? What would the Van 't Hoff factor for that be? 3, yeah, because 1 sulfate anion and 2 sodium ions. All right, so that would be the Van 't Hoff factor. But because we are in 1220 and we are learning advanced skills, is that the Van 't Hoff factor, that we just calculated, the 1, 2, 3, is not always what we observe in lab. We also see deviations from the Van 't Hoff factor. So let's remind ourselves, what is the Van 't Hoff factor for sodium chloride? 2, yes, because you get a sodium and a chloride. So when you think about sodium chloride dissolved in water in a particle level, we got a bunch of sodiums, a bunch of chlorides floating around in solution, all right? This conducts electricity. And so in this picture, what I'm saying is, okay, so for every 1 unit of NaCl I put in water, I get 2 ions out. I get a sodium plus and a chloride minus. But we start to see some deviations from that when the ions themselves start to interact with one another, all right? A sodium cation and anion, are they attracted to one another or repelled from one another? They're attracted, yeah. So if there's a lot of ions present, if there's a lot of cations and anions present, what can happen in solution is for a split second, 2 ions, a cation and anion, can come together and form a neutral, charge neutral sodium chloride particle in that case. This is called the ion pairing effect, where these ions, they actually do interact with one another to an extent, and so what we see is a lowering of the Van 't Hoff factor from ideal conditions. Basically, these ions pair up with one another for a split second to lower that Van 't Hoff factor. All right, and so this is what diverges your Van 't Hoff factor from that predicted value. So let's talk about that ion pairing effect and what factors affect it. Ion pairing will be more abundant. It'll be more, it'll deviate more if your concentration of ions is really high. Because if you think about it, if you have a lot of cations and anions, a high concentration, those particles are closer to one another. So if they're closer to one another, they're more likely to attract and pair up and lower that Van 't Hoff factor for a moment. All right? Versus if you have a really dilute solution, the ions are really far apart from each other, and they're not as likely to pair up. Right? Van 't Hoff factor also increases if your ion charge is really high. Right? Again, extent to pair up in solution. So if you have a +1 -1 pair versus a +2 -2 pair, which pair is more attracted to one another, a +1 -1 or +2 -2? +2 -2, yeah. So ion charges also increases the extent of ion pairing, which again deviates your Van 't Hoff factor. And then finally, ion size. When your ions are really small, they tend to also pair up more likely because you have a really high charge density. Okay, so let's look at these examples here. We got sucrose, NaCl, potassium sulfate, and magnesium sulfate. So here you see the actual observed Van 't Hoff factor for these different solutions. We can go ahead and calculate the limiting value. This is your ideal value. And so if we were just doing, freezing point depression, and I asked you what is I for these, you would say for sucrose it's 1, for NaCl it's 2. What would it be for potassium sulfate? Just the ideal value. 3, and then magnesium sulfate, 2, yes. And so these are our limiting values, but what we actually observe in lab are some of these are lower values, okay? So for NaCl, we see that the actual observed values is lower than 2, but it's most lowered when the concentration is very high. It's very high. So in this high concentration sodium chloride solution, ions are more likely to pair up and do ion pairing to lower that Van 't Hoff factor. If we look at potassium sulfate, we also see a lowering. Again, it's most lowered in the highly concentrated solution, where the 0.001 is dilute, and then the 0.1, we can call that concentrated. And then finally, magnesium sulfate has the most lowering also in the concentrated solution, but let's compare NaCl and magnesium sulfate, because both of them have the same limiting value. Both of them have an ideal Van 't Hoff factor of 2, but which one deviates more at the high concentration? Magnesium sulfate, but why does it deviate more? The charges, yeah, NaCl is the +1 -1 example. Magnesium sulfate is +2 -2. So we see that the ion charges here in magnesium sulfate makes ion pairing more abundant in that solution. So we see that the lowering extent of the mag sulfate solutions are more lowered than NaCl. All right, so I just showed you all of the salt solutions. What's interesting about sucrose? Is there any deviations for sucrose? Interesting. So what did we say? That deviations from the Van 't Hoff factor happen due to what phenomena in water? Ion pairing. So think about it. Why does sucrose not exhibit any deviations from its Van 't Hoff factor? There are no ions, yes. So if we have a non-electrolyte solution, there's no ions, there's going to be no ion pairing, so all these non-electrolyte solutions are actually going to have perfect ideal Van 't Hoff factors because there are no ions for ion pairing to occur. Okay, so let's put this all together and do one more, where we already filled out this chart, all right? The I times M product, we ranked these freezing points from highest to lowest, where magnesium chloride was the lowest freezing point, pure water was the highest, okay? But let's actually consider ion pairing now, because when we did this, we did not consider ion pairing at all right? But that was fine, because none of these values are the same. We can still rank them in terms of highest and lowest, but let's consider where would 0.4 molality sugar appear in this ranking if we consider ion pairing. All right, so sugar has what Van 't Hoff factor? 1, so its I times M product is going to be what? 0.4, yeah. So if we, for a second, if we didn't consider ion pairing, wouldn't 0.4 lay right here on top of sodium chloride? You know, you might think, oh, this sugar solution and this NaCl solution, they're gonna have the same freezing point because they have the same I times M product. But now let's consider ion pairing, okay? So will magnesium chloride have an actual I times M product of 0.6? No, it's going to be adjusted how? It's going to be slightly lower, yeah. So it's going to be slightly lower than 0.6. What about NaCl? Will it have an exact 0.4? Nope, it's going to be slightly lower, yeah. What about the 0.3 sugar? Is it going to exhibit a perfect 0.3 I times M product? Yes, it will. What's different about sugar? No ion, so no ion pairing. So for sugar, it is exactly 0.3. And then the 0.1 sugar will also be exactly 0.1. All right, so with all of that in mind, where will sugar fall? In spot A, B, or C? It's going to be in spot A. Yes, it's going to be in spot A because we ask ourselves, okay, we calculated the I times N product, it's 0.4. For this sugar solution we're adding, is it going to be exactly 0.4? Yes, it will. And so exactly 0.4 will be greater than slightly less than 0.4, all right? And so this is a common exam question that we have where you have to consider ion pairing. We consider ion pairing when two values have the same I times M product. If we just do the I times M product and we get, you know, very different numbers like this, it's fine to just ignore ion pairing and just kind of rank them in terms of their products. But when you have two numbers that are the same, that's when you want to consider ion pairing. Because it may look like, oh, these two solutions will have the same freezing point, but in fact they don't because of ion pairing. Okay, so that's freezing point depression. And then we could rank all of these for boiling point elevation as well. They would just be reversed, where pure water would have the lowest boiling point, magnesium chloride would have the highest boiling point. Because in that case, we're using the same basic equation where it's I times M times a constant, but it's boiling point elevation. All right, so that's freezing point depression. Okay, so let's talk about a different, and I think this is the last, property of solutions. Okay, so I like to call the human bodies big saltwater bags because that's what we are. We are just big bags of water with a little bit of salt dissolved in them. So like when you go to the hospital or whatever and they put an IV bag, they hook up an IV bag to you, all right? And they're pumping liquids into your bloodstream. Is it pure water? No, that would kill you because our body has a certain concentrations of salts in order for certain chemical processes to occur. And so if we're pumping pure water into our bloodstream, it would dilute our body, and that would be really bad and mess up equilibrium due to osmotic pressure. When you change concentrations of salts in your body, you change the osmotic pressure. So what osmotic pressure is, so let me just zoom in on this picture real quick, all right, is when you have two solutions separated by a semi-permeable membrane. So what the semi-permeable membrane means is it separates the two solutions, but it's semi-permeable, meaning that only water can move between both sides, all right? So cells our cells. Those are examples of semi-permeable membranes where only water can penetrate the actual cell walls, but we actually need like certain like holes in the cell to move actual cations or like nutrients inside and outside the cell. But water is absolutely free to move in and outside the cell due to differences in osmotic pressure. All right, so if we have two solutions separated by a semi-permeable membrane, if one side of the solution is pure water and the other side is a salty solution, so there's a high concentration of salts, we say that the salty water exhibits a high osmotic pressure. So what happens is if you let this system come to equilibrium, we have salty water over here, pure water over here. If we just kind of let that system go, what we'll see is that naturally water particles will tend to want to push towards the other side, diluting the other side where it's very, very salty in order to dilute it so both sides are the same concentration. That's what tends to happen naturally over time. And so what osmotic pressure is if I push the water back to the other side, this pressure that I have to push down on the concentrated side is what this solution produces as its osmotic pressure. All right, it's the pressure required to push all of that water back so it doesn't naturally diffuse to the other side. All right, so that is what osmotic pressure is. The trend is that the higher concentration of stuff you have, salt, sugar, whatever, the higher osmotic pressure that you have for that solution. The more force you have to push on that solution to keep water from penetrating in and diffusing to dilute that other side of the semi-permeable membrane. All right, and so we use this equation to calculate osmotic pressure. If you look really closely, this equation is actually just Pivnert, just with different units. So pi is osmotic pressure, where it's equal to, what is this term? The Van 't Hoff factor, yeah, so it's the same one that we talked about previously. N over V, which is moles over volume, so that's molarity, times R. This is the same R we used for gases, so 0.08206, that one. So liter ATM mole Kelvin. And then T, temperature in Kelvin. And so if you calculate osmotic pressure using I times molality times R times temperature, you will get an osmotic pressure in atmospheres, all right? And so what we also see from this equation is that osmotic pressure is equal to I times M times R times T. R is a constant, so osmotic pressure will increase if molarity increases. Osmotic pressure will also increase if temperature increases of your solution. All right? Okay, so do note that this equation does utilize molarity. When we did boiling point, elevation, and depression, what concentration unit do we use there? Molality. When we use the Raoult's law with vapor pressures, what concentration unit do we use? Mole fraction. Yeah, so do be very careful of how we use those units. Okay, so let's do a problem using osmotic pressure. Okay, so you dissolve 2.6 grams of an organic compound, and I tell you it's a non-electrolyte. We dissolve it in water. The final volume of this solution is 250 milliliters. You measure the osmotic pressure of that solution, and it's this. So 0.566 atm, there's your pi, there's your osmotic pressure at this temperature, 25 degrees Celsius, which is 298 Kelvin. Okay, let's calculate the molar mass of this substance in grams per mole. So let's go through this idea. So if this is an organic compound, a non-electrolyte, let's just go ahead and knock out what I is for this. What's it gonna be? 1, perfect, because we'll need that. We'll need that in this equation, osmotic pressure I times M times R times T. So this question is asking for a molar mass in grams per mole. So I always let the unit guide me. The molar mass of this compound is the gram amount of the compound over the mole amount of compound we have. So if I know the gram amount, I know the mole amount, I can get the molar mass. Do I know one of these already? Look at the question. Yeah, we know the gram amount, yes. I like to take inventory, okay, because we're halfway done. We already know half of the equation. So we just need to figure out how the heck do we get the mole amount of the compound. And so it sounds like, okay, yeah, let's go ahead and use the osmotic pressure equation because that's what we're learning right now. This question gives us osmotic pressure. We already calculated what I is. R is a constant and we have a temperature. So it looks like we're calculating its molarity. So let's go ahead and just plug in those numbers to calculate the molarity of this solution that's created. So molarity is equal to pi I, so pi over I times R times T. So we're given that osmotic pressure is 0.566 atmospheres. We already calculated the Van 't Hoff factor is 1, R is 0.08206, liter ATM, mole Kelvin, and then temperature is 298. All right? And so molarity is in the units of moles per liter, or it has the unit of molarity. So if we go ahead and calculate this, put those numbers in, we should already have the unit of molarity. So let's do that. And so we get that the molarity is 0.02146 molarity. Is that the number I put in the denominator? We want a mole amount of compound. This is just a concentration. Yeah, so let's recall, what is the unit of molarity? What does it mean? Moles per liter. So if I had a liter of solution, it would mean I have 0.02146 moles of compound. But do I have a liter of solution? No, I only have 0.25 liters of solution. So we got to do one more step and use the volume that's actually present to calculate how many moles of this compound we actually have dissolved. So I'm going to take the 0.250 liters that's given, the last piece of information I didn't give you, and then utilize molarity. For every 1 liter, there's 0.02146 moles of this compound present. And so in this quarter liter of stuff that we have, there is actually only 0.0057786 moles of compound present. Does this number go in my denominator? Yes, that number goes in the denominator now. So we couldn't just straight take that molarity. We had to utilize the volume that's given to actually calculate a mole amount. And so go ahead and do that. We have all the numbers we need to finish off this calculation. We were already given that we have 2.6 grams of compound. And now we're going to divide by that mole amount we just got. And so then we get a molar mass of 451 grams per mole. Is the approximate molar mass of this organic compound. We're assuming that this is a non-electrolyte, it's an organic compound, all right? Okay, so that's osmotic pressure. Using it and actually it being useful for us to calculate a property such as a molar mass. Like, yes, we could just give you values to plug and chug an osmotic pressure to come out, but like, what does it mean? So a question like this kind of gives it more application, where we can calculate a quantity that's useful for us. So in this case, molar mass. All right, so let's finish off. Okay, wait, no. One more thing about osmotic pressure. I mentioned that cells are, example of semi-permeable membranes where only water can freely move in and out of a cell. So here are some examples of red blood cells and what happens to them when you put them in solutions that either have high osmotic pressure or low osmotic pressure, because a red blood cell exerts a certain osmotic pressure on its own, because red blood cells contain salts within them. They have its own osmotic pressure. But when you put a red blood cell into a saltwater solution, something can happen. If the saltwater solution on the outside of the cell is equal to the same concentration as the inside of the cell, we call that an isotonic solution. That is good, meaning that water is moving freely in and out of the cell, but the cell isn't blowing up with water, and it's also not shrinking on itself. All right, this is when osmotic pressure inside and outside the cell are equal. Our bodies are isotonic solutions. Okay, we don't want water moving in and out drastically outside our cells. So we want all that concentration to remain somewhat equal inside and outside of our cells. All right. On the other hand, if you put a red blood cell in a really, really salty solution where the osmotic pressure on the outside is really, really high, what's going to happen is that the water inside the cell is going to want to dilute the outside water. So your red blood cell is going to shrivel up. So we call this crenation, and then the red blood cell dies. Okay? So this is why you don't drink salt water, because if you drink salt water, the liquid in your body becomes really salty, and then all of your red blood cells are going to shrivel up because all of the water leaves it to try to dilute all that salt that you just ingested into your body. Versus the opposite, all right, if your body becomes too dilute of salts, okay, maybe you drink too much water, what's going to happen is that there's all this excess water, but slightly more concentrated salts on the inside of your red blood cells. So water is going to enter your red blood cells, essentially blowing them up like a balloon, but with water, and then they explode. All right? So this is called hemolysis, where the red blood cells explode, and they get all puffy. All right? And so this is when the osmotic pressure in the liquid itself that the red blood cell is in is very low, so low concentration. So this would be an example of, you know, drinking way, way too much water, which is a concern for like athletes, marathon runners who are constantly drinking water, all right? When you're running a marathon, you can drink water, but what do they also give you in those long races? It's not just pure water, but sometimes they also give you sports drinks, yeah, sports drinks that contain electrolytes, yes, and so that the presence of electrolytes does what to the osmotic pressure of that liquid? It increases it, so it's the same as your red blood cells. So that's the purpose of electrolytes, is to keep our bodies isotonic so our red blood cells don't shrivel up or explode. Okay. All right, and so that's why, you know, dehydration is bad, but also, ingesting a lot of water is also, like pure water is also bad. So, drinking isotonic solutions, sports drinks, can keep your salt balance equal. Though we know sports drinks also contains a lot of sugar, which is bad. So we don't need to only be drinking sports drinks. Drinking a normal amount of water a day is not bad, because we have enough salt in our diets to balance that out. Okay, so that was my attempt at talking about biology. Okay, all right, so let's talk about the last section here, and that's colloids. Okay, no more math. Okay, so we're done with concentrations of stuff, properties. We'll talk about colloids, and this is just kind of an interesting phenomena that happens when we make mixtures and there's matching of intermolecular forces. Okay, so a colloid is a type of mixture. We talked about mixtures and pure substances before in Chemistry 1210. One of the mixtures we talked about is heterogeneous ones. For the most part, we ignore these because these mixtures separate into different phases. So we can also call these mixtures suspensions, meaning that, we can shake up the solution or the mixture. The particles will suspend kind of for a moment, but then settle over time. All right? On the other side of heterogeneous mixtures, we also talked about homogeneous mixtures, solutions. okay? So if we mix salt and water, we know that those two things mix readily. Does salt water look anything different than normal water? No, it doesn't. So we call this a true solution because it's completely uniform versus something like muddy water, okay, settles over time, so that's a heterogeneous mixture, a suspension. So true solutions, things that are completely uniform, do not exhibit the Tyndall effect, which means if I shine a light on a true solution or on true water, like pure water, the light does not interact with any of the particles that are inside the solution. Versus if you shine a light on muddy water, you'll actually see those like dirt particles reflect some of the light, and so you'll actually see the particles, floating down. But if you shine a flashlight on a saltwater solution, do you actually see the sodium and chloride ions floating around? No, we don't. So solutions do not exhibit any light scattering at all. Suspensions do. So the title of this section is called colloids because what's kind of intermediate of these two extremes, true solutions versus heterogeneous mixture, is somewhere in between a colloid. So a colloid is something that looks uniform. It looks like a true solution. An example would be milk. Okay? Milk is the same as your first sip and your last sip. So it's a uniform liquid, all right? But if we look at the particle view of milk, we will see fat globules that are in inconsistent sizes. So a colloid is a mixture, all right, because there's fat mixed in with water, but the particle sizes are very, very, very small where they do not settle over time. But if you look at the particle view, the different fat particles are different sizes, okay? So when you purchase milk, if you look really closely at the label, milk that we buy at the grocery store has two kind of descriptions on it. It can be pasteurized, which means they heat it up to kill any bacteria, but also what's the other word that they oftentimes use on the milk? Homogenized, meaning they mix it like crazy to make the fat particles really, really, really small so they don't settle over time, all right? So what's special about a colloid is it looks uniform, but on the particle level, it's not. And what's cool about colloids is that if you shine light through a colloid, it will, in fact, reflect light, not to an extent where you actually can see the particles like in a suspension, but you can kind of see a beam of light because it's reflecting on the very small particles that aren't settling over time. So here's an example. This could be like salt water, all right, salt water, aqueous, so we're shining a light on it, so see how you can't see the light at all through it, all right? It's not reflecting off of anything because the NaCl particles are so small. But if you shine that same light through a suspension, see how you actually see the beam of light going through, all right? And so that is a consequence of this solution being a colloid. It is not a true solution, and because it exhibits the Tyndall effect due to the fact that there are larger particles in inconsistent sizes. Okay. Okay, ooh, last slide, okay. So an example of a colloid is via soap molecules, okay? So how we wash our dishes, how we do our laundry is due to the presence of these soap particles that can create a colloid solution of micelles. So let's talk about soap for a second, where we're utilizing IMFs again. All right, so we're going to bring that out. We're going to dust those skills off. Talk about IMFs. So soap works as soap because there is a hydrophobic end and a hydrophilic end. So what that just means is hydrophobic means water-fearing, but if we want to put it in terms of intermolecular forces, this is the nonpolar end of the molecule. All right, nonpolar stuff doesn't like water because water is what kind of molecule? Polar, yes. So nonpolar stuff isn't going to interact strongly with water. Hydrophilic means oftentimes means polar, or means is attracted to water, water loving. So if we look at this soap molecule, all right, it's this long fatty acid, you can clearly see that this is the nonpolar side of the molecule, and then this is the hydrophilic part of the molecule. It's polar, but it's also ionic. Does water like polar stuff? Yes. Does water like ionic stuff? Yes, but why? Why? Why does water like ionic stuff? For which IMF explains that? Ion dipole, yes, ion dipole, yes. So, and hydrogen bonding to an extent. So we see that in a soap particle, water interacts with this end of the soap. Then what's going to interact with this end? What's the purpose of soap? Clean stuff. Clean stuff, especially grease or oil, right? Can you wash your oily hands with just water alone? Nope, you got to use soap, because that soap interacts with the nonpolar parts of the oil, and then the polar part of the soap interacts with the water so it can be washed away, right? So that's the purpose of soap. That's how it works. You can see that in this picture where all of these little snake-looking things, the nonpolar end, the hydrophobic end, is interacting with the oil droplet, where the ionic polar ends of the soap are interacting with the water, so it can move your soap or your oil away from wherever you're washing it away from. All right, so at a certain concentration, if you make a soapy mixture, you can make a colloid. So soap particles, if you just have a pure soap mixture, you just mix soap and water with nothing else. So if you have a bunch of these molecules, what you can make are these kind of globs of soap. Where all of the nonpolar ends congregate towards the bottom or in the middle of this, what we call a micelle, and the outside is all of the polar ionic ends of your soap. All right, and so on the outside, your micelle is interacting with water, but on the inside, the nonpolar center can grab those oil droplets or grease or whatever you're trying to clean away from wherever you're taking it. So you might have, heard the idea or phrase micelle previously. So anyone use this at night? Yeah, what's that called? Micellar water, yeah. It also contains micelles. So really what you're buying, if you're washing your face with this micellar water, is soapy water, where it contains micelles, all right? Micelles meaning that we have a bunch of these little features of soap molecules all congregated with one another. But since we have a ton of these in micellar water, they're all different sizes. Okay, so it's not a true solution, right? So when you have a solution filled with micelles, it's actually a colloid, all right? So this micellar water, this mixture of soap, is actually a colloid. So will it exhibit the Tyndall effect? If I shine a laser pointer through this solution, will you see a straight beam of light? Yes, you will. All right, and I have a bottle of micellar water in my office to test this out, but I forgot my laser pointer, so I didn't bring it. But I can bring it next time and show you that, yes, in fact, if you shine a laser through micellar water, you will see the Tyndall effect. But if I take pure water or salt water, will you see that beam of light? No, you won't, because those are true solutions. Well, not pure water, but there's no colloid or no micelles to scatter that light. Okay, so that's makeup. Okay, so that ends on chapter 13. Okay, so what does that mean about chapter 13 homework? It is due on Monday at midnight. Yep, and so I think looking at the estimated time, it's a 2-hour homework set. That's what you should anticipate for homework sets. But again, remember, a due date does not mean due date. You don't have to do it on Monday. Hopefully, we're 2 weeks into the semester now. Hopefully you've done some of the questions by now. Okay, so we are going to move on to chapter 14. All right, so grab those slides from the thing. Yep. And we'll start. Okay, so this is the beginning of K. We're going to talk about K for a long time. We're going to talk about 2 different Ks. So in this chapter, we're going to talk about small k, baby K, little k. This is rate constant. Next chapter, we're going to talk about big K, which is equilibrium constant. So just understand that. So this chapter is split up into 2 homework sets, which is separated by midterms, because I want to be nice to you. All right, so midterm 1 covers these 3 sections: rate laws, reaction rates, the integrated rate law, the Arrhenius equation. Midterm 2 is going to cover reaction mechanisms and catalysis. So slide 48 is what separates these. I have it in the slides itself, but I will make a big show of it that, hey, midterm 1 material ends here. We're going to keep going, but understand that for midterm 1, we will not assess reaction mechanisms or catalysis on it. All right. My plan is to get my practice exams posted this weekend. That's my plan. I don't know about the department midterm, practice midterms. I need to go looking for them. I don't know where they are yet, but I will post them. Okay, because our exam's in 2 weeks. 2 weeks. We have 48 slides to get through. Okay, so the title of this chapter is Chemical Kinetics, meaning we're studying how fast reactions go. Some reactions happen fast, some happen slow. Okay, so like this reaction, which I will do, the hydrogen balloon reaction, what would you call that reaction? Is it fast or slow? Fast, yeah, it's pretty fast, and we'll check. You want to check if it's fast? Yeah, let's check. But then, like, let me think of another chemical reaction. Rusting on a car, all right? The process of oxidation, oxidizing iron to iron oxide, is that fast or slow? It's relatively slow compared to a hydrogen balloon, right? And so that's what we're studying, the extent of how fast reactions go. So let's use our intuition a little bit, all right? So the big idea of reactions happen when particles collide. In order for a reaction to happen between A and B, for A and B to become C, like in this reaction, all right? Those A and B particles, they have to collide with one another with enough energy to produce a product. That's the big idea of chemical kinetics. How can we change collisions, the extent or energy of collisions, to make a chemical reaction proceed forward, all right? So there's a lot of factors that lead to speeding up or slowing down reactions. So with the idea of collisions in mind, think about how does the concentration of your reactants, your concentrations of A and B, affect reaction rates? So which one will result in a faster reaction? High concentration of reactants or low concentration? High, yeah. Okay, so if I have all of my reactants really close to me, I can, get them to collide much, much more often than if the reactants were spread across the entire campus or something. All right, if the idea here is I had to bring these things together for a reaction to happen, it's going to happen more quickly if they're really close by to one another. And that happens at high concentration. All right, what about temperature? High or low temperature will the faster reaction occur? High. Why? Particles are moving faster, yes. So relate that to collisions. All right, physical states of reactants. Which one is going to have the fastest reaction between solids, liquids, or gases? Gases, why? They're moving around like crazy idiots, versus in the solid phase, they're kind of separate, just hanging out. It's harder to get those, like a solid over here and a solid over here, to interact. Kind of like rusting on a car, right? Iron is a solid. It does have to interact with a gas, but it's relatively slow. All right, and then just think about this, the idea of the word catalyst. Okay, catalyst. People use that in like regular language too, not just sciences, but presence of a catalyst. Do you think if a catalyst is present or not present, which one has a faster reaction? It's present, yeah. Because oftentimes we use that in language like blah, blah, blah was the catalyst for, my passion for chemistry or something like that, Okay, and then finally, let's test this out. A reaction between 2 solids or 2 gases, which one's faster? 2 gases, yes, because they're moving a lot more. So let's just test this. Let's test this to just make sure the reaction is fast. Okay, so in a hydrogen balloon, did they write what's in here? Yes, 2 equivalences of H2 gas and 1 equivalence of oxygen gas. So in this reaction, everything is in the gas phase. All the particles are moving. Quick question, are all the particles moving at the same speed in this gas, in this balloon? No, they follow the Boltzmann distribution. Also, hydrogen and oxygen have different molar masses, so they have different Boltzmann distributions. Okay, all right. So let's test this out. So this time I actually did get them to put oxygen in it, so it should be fairly loud. All right, so let's test this. So remember, everyone, ears. This will be louder than previous time. So let's try this. Okay, ears, everyone. Yes, let's all wake up. Wake up. Yeah, because the first one, the one I did on the first week of classes didn't have oxygen in it. All right, so it wasn't as loud, so that one was louder. Okay, so was that reaction fast? Yes, it was fast. So it has a relatively high rate constant, which we'll learn about here soon. Okay. All right, are we awake now? Yes. All right. Okay. So which vessel do you think will have the fastest reaction rate? Assume they all are at the same temperature. 1, 2, or 3? 2. For what reasons? More concentration, but also it's a gas. Yes, because 3 is also a gas, but the particles are further away from one another. They're not going to be making as many collisions. Okay. All right, so let's talk about reaction rates. This is something we haven't really discussed too much in previous times. Whenever we look at chemical reactions, we just kind of look at the stoichiometry. All right, so for this chemical reaction, you know, that 1 unit of this molecule is combining with 1 unit of water to produce 1 unit of this product and 1 unit of HCl. We've done stoichiometry. We could do a BCA table to say, oh, if I react 5 moles of this, I get 5 moles of that out. That's what we've done previously. Now we're thinking about how much stuff are we making or consuming, but with time now. All right, so we can relate the rate of consumption of a reactant to the rate of consumption of another reactant to the rate of production of a product and all of the other products. So for example, this graph is showing how the concentration of this reactant is changing over time during the course of this reaction. So if you think about converting reactants to products, yes, we are consuming reactants. So if we consume reactants, the concentration decreases with time. But let's just note here, is the concentration decreasing with time in a constant rate? No, it's not. It looks like the reaction is slowing down. That kind of sounds like calculus, right? Yes, it does. So we'll come back to that idea. But this graph is just showing, yes, that this product or this reactant is being consumed with time. But at the same time, we could draw another graph for the production of HCl. But the graph for HCl will be the opposite direction because it's being produced with time. And that's how we can track, okay, concentration changes with time. And that's how we get rate. All right, so the rate of change for this reaction, we can say the consumption of this reactant. Let me highlight some stuff so you can see it. This reactant, the rate of change for the consumption of this reactant, notice the negative sign because it's a reactant and it's being consumed, is equal to the production of this product. And so note that the relationship here is 1 to 1. And the reason the relationship between these two reactants and products is 1 to 1 is because the stoichiometry in the balanced reaction is 1 to 1 as well. So we see that stoichiometry is important here. And so we can make a reaction relationship for any reaction based upon the stoichiometry. So let's say we combine some amount of A, B to give C and D. We can make any ratio or any comparison between consumption or production for any one of the reactants or products using this generic equation. But what you basically want to see here is that A and B are reactants, they're being consumed, so note that there's a negative sign in this reaction rate, versus C and D are products, so they're being produced. So there's a positive sign there, right? And so what we can also see here is that the stoichiometry, so like the little a, little b, the stoichiometry here, if there is stoichiometry in your equation where it's not just a 1-to-1 ratio, any stoichiometry in your balanced equation becomes in like the denominator of your rate equation. So for example, if I had two a's combining with a b, in this rate equation, I would put a 2 in the denominator. If this was a 3 B, like 2 A's combined with 3 B's, there would be a 3 in the denominator there. All right, in order for all of these rates to be equivalent to one another to an overall rate. All right, so that is rates, but let's just use our intuition a little bit, okay? You know, when I'm teaching this right now in 1250, chemical reactions, stoichiometry, and all of that, okay? And so I often talk about making sandwiches. 2 breads plus 1 cheese gives us a sandwich. This is stoichiometry that we've looked at in 1210 to understand BCA tables and all of that. So I'm bringing this reaction back, but now talking about reaction rates. So let's just use our intuition a little bit. If we're making sandwiches and the average rate of consumption, think of it like a speed, okay? The speed at which I'm consuming bread is -10 breads per minute. What is the average rate of productions of sandwiches at the same time? What do you think? 5. Yeah, because if I am consuming 10 breads per minute, I need 2 breads to make a sandwich, so I should be making 5 sandwiches per minute. How did you get 5? You used what part of this reaction? The ratio. You see, oh yeah, 2 sandwiches, I need twice as many breads to make a sandwich, so it's 5 sandwiches per minute, all right? So if we wanted to make a relationship for all of this, we would write, actually for completeness, okay, so we make 5 sandwiches per minute. What about cheese? 5 cheese, but be careful with the sign. It's going to be -5 cheese per minute because it is being consumed, all right? So putting it all together, all of the rates at this time, or this average time, we will have -10 breads being consumed per minute. We will have 5 cheeses being consumed per minute to produce 5 sandwiches per minute. So let's get the full rate equation here, rate relationship, and see how these numbers fit in. So the rate for this reaction is negative the change in bread per minute, or I guess per time, so delta T. So that's the rate, that's this rate actually, but over 2 because of the 2 subscripts. So I want to put 1 over 2. Or the stoichiometry. So that 2 now becomes a 2 in the denominator. So we need that 2 there because if I want to set this equal to the next rate for the next reactant, I'm going to write negative change in cheese over time. But this time, the fraction that goes on the outside is just 1 over 1 because the stoichiometry is 1. Equals, now since I'm looking at a product, sandwiches, I don't need the negative sign, it's going to be positive, but it's still going to be change in sandwiches over time, 1 over 1 because the stoichiometry is 1 over 1, right? So that is the full relationship for this reaction, right? So the purpose of this relationship is now I can put all of these numbers into this relationship and they should all be equal to one another. So let's just do that real quick. So I am putting these values, right, that value into these, parentheses here, the delta component over time. So I'll show you. -1/2 over 10 equals -1 over 1 over -5 equals positive 1 over 1 times 5. Is this relationship true? Yes, it's 5 equals 5 equals 5. All right, and so this is how, you know, we kind of just use our intuition with the stoichiometry here, but if you put it into this equation, all of it works out as well. Okay, so let's do one with actual chemistry. Okay. All right, so this is a different reaction. So two HIs are becoming H2 and I2. So if the initial rate of consumption of HI, this should be a negative, because it's being consumed, is negative 0.24 molarity per second. What is the instantaneous rate of appearance of a product? Boom, that of H2 at the same time. What do we think? Just think bread and cheese. It's going to be positive 0.12 molarity per second, all right? Because HI is being consumed twice as fast as that one product is being produced, because it's a 2-to-1 ratio. You can think, oh, I consume 2 breads, I get 1 sandwich out, so we're gonna have that molarity here. So that is for H2. All right, let's do another one. What if the rate of appearance for H2 is 36 torr per second? So remember, these are gases. So I can express a gas in terms of its pressure or its molarity. And so that's what I did in the first one, molarity. But for gases, pressure is actually just proportional to molarity. And you can rearrange Pivnert to prove that. Pressure equals N over V, which is molarity, times RT, which is a constant. So in this case, you can just treat 36 torr as its concentration, all right? So if H2 is appearing at 36 torr per second, how will the concentration of the disappearance of HI change over time? It's by a factor of 2, but it's going to be double, yeah. So we're actually going to see a negative, 72 torr per second. Yeah. So if H2 is appearing at 36 torr per second, you have to consume twice as much HI at the same time in order for that to happen. So we have to double the rate there. Right, and so if we want to write the full relationship here, just like before, the numerator is the stoichiometry in the equation. So in this case, negative 1/2 change in HI concentration over time equals positive 1 over 1 H2 concentration over time equals positive 1 over 1, because stoichiometry is 1, change in I2 over time. And again, what we just calculated is what's in the parentheses here. That's the relationship that we just looked at in the 2 previous equations. If you know one of them, you know the rest of them. Okay, cool, we got 7 minutes. Okay, so let's look at this graph. Okay. Same reaction. So I'm going to tell you that this reaction is the change in H2 concentration over time. The concentration is increasing for this thing. So without even looking at the equation, H2 is most likely what? A reactant or product? A product, because it's being produced. Concentration is increasing, so it's going to be a product. Okay. All right, so let's put it together. What substance is going to have a similar graph to this H2 graph? I2, yes, because it's also a product, all right, it's also a product, and it also has a 1-to-1 ratio. So this graph actually will look the same for H2 and I2. For every H2 that I get, I should also get an I2 also. Okay, what do you think the graph for the reactant will look like for HI? Will it look the same as this graph? Its change in concentration over time? No, because there's a couple things. HI is a reactant, all right? Also, the stoichiometry is different, so let's think about how that will change what the graph will look like. So will the graph have a positive or negative slope? Negative, because it is a reactant and it's being consumed with time. And then what do you think its steepness will look like? How will its rate or its change in concentration differ in terms of the graph that I'm showing right here, H2? Will it be the same steepness, steeper, not as steep? Steeper, yeah. Steeper implies, faster rate in this case, but in faster rate of consumption. Yes, because it's faster rate of consumption. So what it would look like is, I don't know, something like this, I guess. Steeper and negative slope. All right, that is what HI will look like. I think I have it on the next slide. Yes, I do. Oh, wow, that's pretty good. Okay. All right, so that's putting it all together where H2 and I2 will have the same looking concentration graphs with time. HI has a negative slope and it's steeper because the stoichiometry is different. All right, so according to this graph, and I have the full rate expression at the bottom that we calculated previously, where stoichiometry is at the bottom, right? According to this graph, at any particular point in time, the what of the H2 graph versus the HI graph will be split in half. Will the concentration at any certain time be half, or will the slope be half? It's going to be the slope, because slope here infers rate, right? That HI is being consumed twice as fast as other things are being produced, so the rates are cut in half, not the overall concentration. All right, so the big idea here is that rates are related to stoichiometry. The rates of your different consumption or production of your different things will be related by stoichiometry. Okay. So, one more here. Let's put it all together. Consider this graph. I got a substance changing its concentration over time. What can we deduce about this reaction? Is X, is it a reactant? Is it a product? And is this reaction speeding up with time, or is it slowing down? What do we think? Okay, so let's go through the guiding questions here. Is X being consumed or produced in this reaction? Produced, so we can then go ahead and eliminate A and B. Cool. Now we need to decide, is the reaction speeding up or slowing down? So yes, the concentration's going up, but rate is not concentration. Rate on this graph is actually what property of this graph? It's the slope. So let's look at point 1, has a instantaneous slope, a tangent that looks like this. That's pretty steep. But what's the tangent at point 3 later in the reaction? How's the rate changing? It's actually decreasing with time. Yeah, so it looks like the rate is actually getting slower with time. So this reaction is slowing down with time, so D. All right. It's slowing down with time, or you can think, oh, yes, the concentration is increasing with time, but as you get far out in time, the change in concentration is not increasing as fast as previously. All right, so that's how we infer a graph. So don't have enough time to move on to the next section, so when we get back next week on Tuesday, we will start rate laws. Have a great weekend, everyone.